So good morning and welcome everyone. Thank you so much for joining us today. My name is Alyssa Sleva. I'm the head of marketing for Prescient Transmission Systems. Prescient is an electrical engineering consulting firm specializing in risk assessments and next generation concepts for the electric power grid. This is the second in a series of webinars that Prescient is presenting on electric power industry topics. So we ask that everyone remain muted for the duration of the webinar, and then at the end we will have an open Q&A section, at which time you're welcome to unmute yourself. You can also submit questions via the chat throughout the presentation, and I'll be monitoring that and bringing questions forward at the end. And now I'll turn it over to our keynote speaker, Tony Sleva, President of Prescient.
Thank you for attending today's presentation on wide area blackouts. I'm president of Prescient Transmission System. I've worked in every area of transmission system design and operation. I've worked in energy control centers. I've worked in design. I've worked as a substation repairman. And I also teach courses for the University of Wisconsin-Milwaukee. The way I got involved in wide area blackouts is I used to work in nuclear power. And when I worked in nuclear power, one of the issues that came up was station blackout, where the NRC said that nuclear power plants had to evaluate the possibility of having a complete power outage or AC power outage at a nuclear power plant. And we were obligated to study that because it was an NRC requirement. And so when I think about this, I've been working with wide area blackouts for 40 years now, because I started in nuclear power in the 1980s. This would be to 2020, this is 40 years of wide area blackouts. And I'm certain the models are very appropriate for steam turbine generators and combustion turbine generators that are powered by jet engines. The big risk I see is that we haven't really reached out and understood and did the tie between transmission systems and distribution systems and the customer loads that are connected down at the just off the distribution lines. When I'm starting to think about wide area blackouts, we're thinking about interrupting 250,000 customers at the same time. That's a major metropolitan area that we're worried about interrupting. And the thing we're worried about the most or most concerned about are three-phase faults on transmission facilities. The distribution lines that serve neighborhoods, the most you'll interrupt there is maybe 10,000 customers. We're worried about the big hits where I've got a $250,000 or 250,000 customer interruption. And the risk factor we're really worried about are peak summer loads. The loads on the electrical system change hourly and they change yearly. And the most severe loading is during summer load conditions. The prevention strategies we're thinking about are enhanced system models and enhanced simulations. Stage fault testing. We'd like to see stage fault testing routinely conducted by electric utilities. We're also thinking of adding some new relaying schemes, power factor biased under voltage load shedding. We're also thinking about traditional load shedding that just the facilities are overloaded, we automatically shed load. And we're thinking about rapid voltage recovery. When a fault occurs today, it takes 100 milliseconds more or less to clear the fault, and you've got a voltage dip for 100 milliseconds. We'd like to see the voltage dip reduced to possibly 8 milliseconds. The reason why we're concerned about triggers is normally the energy production and the energy consumption is balanced. It's a steady state balance. When faults occur, the balance is disturbed and all the power we're producing is not transmitted. And since it's not all transmitted, it's not all received. That means that we're going to be storing more kinetic energy in machines during a fault, and we're going to be have a shortfall of energy at the consumer end. The problem that we're really concerned with is after the fault is cleared. So I've got the system running under normal configuration. I have a transient that lasts, a fault that lasts 100 milliseconds, and then I clear the fault. And when I clear the fault, the energy production could be 110% of what it was before the fault occurred, but the energy consumption could be 120%. So I've got a mismatch during recovery of production and consumption. And the reason why we're concerned about triggers is we think of the electrical system as being a single machine. It's connected with many drivers and many takeoffs, but it's a single machine from the Atlantic Ocean to the Rocky Mountains. The couplings are electromagnetic rather than gears and shafts, but the triggers distort the coupling between the energy producers and the energy consumers. The best way to look at it from an engineering point of view is what the trigger does. Power transfer across the system is a function of voltage, sending end voltage and receiving end voltage. And on the electrical system, we have to provide two things. One is real power, which is kilowatts. And the second is excitation energy, which is the VARs we're putting on the system. Both of these are impacted when we hit a low voltage limit. It impacts power transfer, it impacts excitation energy transfer. When I think of traditional power plants, I think of machine-based power plants. A machine-based power plant would be a typical steam turbine generator. This figure here is showing the turbines driving a generator. When I look at wind turbines are typically machine-based. But now we're introducing power electronics-based systems. So when I'm looking at solar panels on rooftops or solar farms, I'm looking at power electronics-based systems. And they're going to respond differently than the traditional power plants. So what we have to do is we have to make sure we've got all our power electronics-based power production facilities in all our models. When I'm looking at things like this, if I look at how I produce energy, this graph here shows the energy production capability of a steam turbine generator. Megawatts are the dashed lines. MVAR is the solid line. And on any given day, I'm operating at a certain operating point. Under a peak load condition, I may be operating this 500 MVA unit at 400 megawatts. On a light load day, I may be operating the same unit down here at condition 5, which would be 250 megawatts. So the amount of power I'm producing by a machine is based on the amount of energy I'm selling. When I look at the MVAR capability, this machine could put out, at condition 9, it can put out a little over 200 MVAR. And if I unload the machine, I can push 300 MVAR. These are steady state load values on the machine. The capability is 200, but typically I'm operating the machine down here close to 0 MVAR because the generating people want to operate the most efficient generator they can. And if I'm not pushing MVAR out of the machine, my I squared R losses are lower, and I'm operating close to 0 MVAR on my machine. And that's good because that means I have MVAR capability when a transient occurs. So the electrical loads I have fans and pumps, I have lights and heaters, I have air conditioners. Air conditioners are a problem because these are positive displacement pumps. They're very high torque loads, and I'm putting shunt capacitors throughout my transmission and my distribution system to provide the VARs I need. When I start looking at the loads, it's important that I look at the mechanical characteristics as well as the electrical characteristics. And so what I did is I put down, this is a speed torque curve for a typical fan and a typical motor. And what happens is if you look at the fan characteristic here in orange, as the fan speed changes, the torque requirements change. But the motor characteristic is a function of the terminal voltage on the motor. If I have 100% terminal voltage on the motor, the blue line is how much torque the motor can produce. And the intersection of this, the fan curve and the motor curve is the operating speed of the motor. So typically I'm looking at induction motors, and at 100% voltage, they're operating somewhere around 96% of synchronous speed. If the voltage drops down to 70%, I'm going to be operating here at 91% speed. So the power demand of a motor is a function of the terminal voltage you put on the motor and the terminal voltage determines the intersection of the fan curve and the motor curve. When I look at air conditioners have the same characteristics, except I have to add another characteristic in here. And this is the positive displacement history curve for the motor, for the compressor. Once I get the air conditioner running, I have to maintain 80% in order to have the air conditioner not stall. So what happens is when I get to 70% voltage for more than 50 milliseconds, air conditioners start stalling, and they don't resume normal operation until the fluid evaporates. And the problem you have is when I'm looking at a fan and I'm at 70% voltage on the motor, I've got, at low speed, I've got a lot of difference between the fan curve and the motor curve. When I'm looking at an air conditioner motor where I've got fluid that I'm trying to evaporate, I've got a very small delta between the torque that's needed and the torque that's available. And this means that when I'm reaccelerating, I'm going to be putting a lot of energy in the motor for a long period of time. And normally a motor that would start in 2 seconds may not start for 20 seconds. And that means I've got a voltage dip that's going to be out there for a long, long time. Another thing that's important to recognize is the time of the year. The loads on the power system change daily, they change hourly. And what I'm trying to show on this graph is that if I look at the spring day here, the load on a spring day is about 70%. Under a peak load condition, summer loads on this circuit, the load is up to about 95%. So the difference between 95% and 70%, this is a 25% increase in load, and that's due to people turning on their air conditioners. I'm looking at recovery conditions, and that's what we're really focused on, preventing wide area blackouts by understanding the recovery conditions. Generators producing 100% power, the motors are consuming on the order of 60% power, and other loads are consuming 40% power. When a fault occurs, the existing models show minor motor reacceleration, and we're recommending that you have significant motor reacceleration. And the way you've determined that you need significant motor reacceleration is you have to understand the geographical spread of the voltage dip. A minute ago, we showed a steady state megawatt megavar curve for a steam turbine generator. And what this curve is showing you is a transient condition on the steam turbine generator. When a fault occurs, the voltage goes to zero. When the voltage goes to zero, mechanically the machine is still trying to produce, in this case, 500 megawatts, but it can't produce 500 megawatts because it can't transmit through a zero voltage point. 100 milliseconds, the fault is cleared, and the kinetic energy can come out of the machine, and the machine can put out more than its rating for some short period of time. And here I'm showing it's 10 seconds. The machine can also put out a lot of MVAR, a lot more MVAR for a short period of time. The only thing that's going to limit the MVAR capability is the machines come with VAR limiters, and the VAR limiter is going to kick in somewhere around 10 seconds. So this is showing the machine can produce, for a short period of time, it can produce much more energy than it can produce under steady state conditions. I'm looking at this, and how do I tie it all together? Well, I'm going to look at pre-event conditions, and I'm going to look at recovery conditions. And this is a wide area blackout. So wide area blackout means we're talking about very high amounts of load. So we're looking at maybe 8,000 megawatts of load in this analysis, and the power production facilities aren't producing any MVAR. All the MVAR that I need for the system is coming from shunt capacitors. So I've got 3,800 MVAR of load, which I'm supplying from capacitors, 8,000 megawatts of energy that I'm supplying from generation facilities. When a fault occurs, the recovery megawatts could be 8,800. So the recovery megawatts are 10% higher than the pre-fault load. But the machines can produce 5,200 MVAR. They have the capability of producing 5,200 MVAR in pre-event, but we were taking capacitors rather than machines providing it. When the voltage drops because of the transient that occurred, the MVAR capability of the capacitors is reduced. So I went from 3,800 MVAR of capacitance to 2,500. So that says as soon as the fault is cleared, in the simulation I have here, I have 7,700 MVAR available for re-energizing and reaccelerating motors. The problem that we come up with is under normal conditions, the demand was 3,800 MVAR. If I'm just trying to reaccelerate 10% of my load that's out there, the new MVAR demand is 10,000. So if the new MVAR demand is 10,000 and the capability is 7,700, this is the type thing that leads to a wide area blackout, because I don't have enough of MVAR to get all my machines reaccelerated. If the voltage dip persists too long, what happens is the auxiliary systems in the traditional power plants start tripping out on low voltage. And when that happens, once I'm having trouble recovering and I trip my first power plant off, then that's going to be a cascade. So reacceleration is a function of the fault location. If I have a fault in a major city, like I have a fault in downtown Philadelphia, I'm going to shed load in Philadelphia, and I'm not going to get a large inrush for recovery. If the fault isn't in Philadelphia, though, let's say the fault is in Allentown, Pennsylvania. If it's in Allentown, Pennsylvania, a three-phase fault there will be seen in Philadelphia, and that's the type of thing that's causing the recovery transient. The geographical spread of the voltage dip, what I have to do is plot voltages over a geographical map of the area so that I can get an understanding of what's going to reaccelerate. And fault clearing time is important. 100 milliseconds is typical clearing time for three-phase faults on high voltage systems. And the reason why 100 milliseconds is key is that's a couple revolutions of a 1200 RPM motor. So you want to know the connected loads. Are the connected loads air conditioners or are they fans? And you want to know what the fault clearing time is. The risk factors on power production facilities. Traditional plants are well understood. Machine-based production facilities are well understood. We have excitation systems that can increase the MVAR output. We can release kinetic energy as megawatts. The power electronics based need additional modeling and additional studying. A lot of the power electronics based are on homeowners' rooftops, and we have to make sure we've got all of those represented at each substation in a lumped model. If I look at the simulations, the traditional models I have show constant resistance loads, constant power motors, high torque motors, capacitors, and other loads. For the reacceleration model, what you have to do is you have to add this new line, high torque motors reaccelerating. And the tipping point when you go from the traditional model to the reacceleration model, if the fault voltage decays to less than 70% in an area, then you're going to a reacceleration model. And if the duration is greater than 100 milliseconds, you've got to go to the reacceleration model. We're looking at the timelines. Short circuits with rapid fault clearing, less than 100 milliseconds to clear the fault. If you get a short circuit where a circuit breaker sticks, one that fails to open on command, typically we're looking at somewhere around 250 milliseconds. And now the other thing we have to worry about today is substation sabotage. If the substation is sabotaged, it's probably going to take 10 seconds to clear the event off the grid. And we base these times based on what we've seen happening on the system. On April 7th of 2015, there was a near miss. There was a fault on a three-phase fault on a 230 kV transmission line that persisted for 58 seconds. The only reason why this didn't progress to a wide area blackout is it happened in April. If the same condition had occurred in July instead of April, we would have had a major blackout. And September 8th in 2011, they did have a wide area blackout. The short circuit that initiated the event was cleared in 67 milliseconds, and it turned out that it was a 500 kV line fault caused by a switching error. So the numbers for the times we look out here, these are actually tied into events that we've investigated on the power grid. The strategies that I need to stop wide area blackouts: I need enhanced system models and simulations. I need bifurcated models, and the bifurcated models have to look at fault recovery conditions, and they have to include power electronic based energy source modeling. I also need to do staged fault testing. I've been in the industry for 50 years, and it's been 40 years since I participated in a staged fault test. We should be demonstrating that all our protective relaying systems that we put in for the system meet their design requirements by doing a staged fault test as part of all new facilities that are energized. And in addition to that, we should be doing type testing. Type 2 tests are demonstrating that our load models and our simulations are relevant. So I'm thinking we should do one yearly staged fault test per an ERC region per year. So this is in addition to staged fault tests we do every time we add a new facility. And this would prove that all the calculations and all the simulations we've done are relevant and appropriate. And another thing we want to see put on is power factor biased under voltage load shedding. And what we've done is we developed some relay characteristics to show that. The under voltage devices I use now today are simple change of state items. If voltage drops below 90% there, and for 2 seconds or something like that, the relay would operate. And we're thinking that you need power factor biased under voltage trip curves. If I have a really poor power factor, that's what I'm showing here. This is a group 1 setting. So group 1 has 4 characteristics. It has 100% power factor, 90, 80, and 70% power factor. And if I'm at 90% voltage, and I should say 80% voltage, and 90% power factor, that would be right here. I can allow this to run for a longer time than if I've got a poorer power factor. If I've got a poorer power factor, what's that telling me is a lot of motors are reaccelerating. And if all the motors are reaccelerating simultaneously, that's a huge VAR demand on the system. So rather than taking that huge VAR demand, I should start shedding load, and that'll give me step increases in voltage and allow the voltage to recover quickly. I'm showing 2 characteristics here, a group 1 and a group 2. And this is just showing that if I change the time delay, this is a nominal time delay of 3 seconds. If I want to change the time delay to 6 seconds, what I do is I change the position of all my curves. So this was the 70% curve, 70% power factor curve starting with a 3-second delay. And this is the 70% power factor curve starting with a 6-second delay. The prevention strategies have to include load shedding. Right now, all my protective systems are set up to allow overloads to occur indefinitely. And we would like to put in load shedding. So if I get 150% of a facility rating, I start doing load shedding at 10 seconds if I'm using the group 1 under voltage settings. And I would start doing load shedding at 15 seconds if I'm using the group 2 under voltage. If I get a facility rate loaded to 200% of rating, 200% of rating is a severe overload. That's going to cause the conductors to heat up and possibly sag down into something. So I should start shedding load at 2 seconds. And when I'm looking at load shedding as something like this, I'm looking at control center enabled load shedding, because I'm not looking at tripping the facility that's got the overload. I'm looking at tripping neighborhood substations. So if I trip loads in neighborhoods, I'd reduce the impact on the power grid and reduce the possibility of a wide area blackout. Rapid voltage recovery is something else that's near and dear to us. When I look at rapid voltage recovery, I'm thinking of solenoid type series reactors. This is a prototype that we've built. This is a 200 amp 15 kV solenoid series reactor. And what happens is when these operate, they change the impedance of the power system, and they allow voltage recovery in 8 milliseconds. The fault is still on the system for 100 milliseconds, but the voltage recovered. This graph here is showing time voltage profiles for faults on a system. And the area of concern that we have right now is the yellow envelope here. A fault occurs at time 0. It takes maybe 80 milliseconds for the fault to clear. And after the fault is cleared, I slowly recover from that condition. This is showing the fault is near bus A, which is the bottom line. But this is an impact that goes throughout the power grid. It impacts bus B and bus C. If you install solenoid type series reactors, the concern moves from the big yellow to the little pink here. Anyhow, this is the same system with solenoid series reactors. Now these are put in series with transmission circuit breakers in substations. And this is showing that in 8 milliseconds, voltage recovers from 0 at bus A to 70% and to 80% at bus B and to 90% at bus C. And this gray area here is now the fault is still on the system. The circuit breakers haven't isolated the fault, but the system impedance was changed by the solenoid series reactors, and I changed the voltage transient to an 8 millisecond transient. When I only have an 8 millisecond transient, I no longer have recovery that I have to worry about because I haven't allowed motors to slow down for 100 milliseconds. So I'm looking at this, when we do blackout risk analysis, the calculations that have to consider the transmission system configurations, it turns out the more lines you add, the more risk you add. Because what happens if you have a 500 kV line that runs from Baltimore to Washington, D.C., if you add another line, between a 500 kV line between Baltimore and Washington, D.C., you've changed the impedance on the system and you've spread the geographical area. So you have to know the load data and the load flow models, and you have to look at the short circuit models. So this is a iterative type calculation. And the deliverables that we're looking at is whether the system is going to recover after a significant event, what you have to do to make every significant event recoverable. By the way, we do training in partnership with the University of Wisconsin-Milwaukee. So we can create next generation simulations, and we can teach clients how to do next generation simulations and identify weaknesses before a wide area blackouts occur and address the weaknesses so that we'll never have another wide area blackout. Everyone has to understand the risk, the consequences, and the changes that can be implemented. I think in terms of Verizon brags that they're using their 5G technology. I think that the electric power companies are still using 2G technology, and we have to implement things to get to 5th generation technology on the electric power grid.
Somebody put into the chat, please explain stage protect test.
Oh, stage fault test maybe? What we would like to do is we build substations, transmission lines, and distribution lines, and we put in protective relaying schemes, and we test everything, and then we go away and cross our fingers. The real test of how good we did is when a thunderstorm comes through and lightning strikes a line. And when lightning strikes the line, that's the first real test, and that's a natural fault test. And I would like to see stage fault tests done where someone actually energizes a transmission line and then inserts a 3-phase ground on a transmission line and verifies that not only did the circuit breakers open on both ends of the transmission line, but the system recovered and there was not a unrecoverable transient. Right now, we're just doing these things by calculation and by simulation, and we're not actually putting faults on the system to see if that happens.
What would be the mitigation actions if something actually does go wrong, right? So you're fault in a line, if your protection is not as good as you thought it was, and something should go wrong, what would you implement as a possible mitigation measure to say that this stage test go wrong?
Oh, yes. Good question. When I think of a stage fault test, I don't think of someone taking a 4-aught copper wire and throwing it over the transmission line. I think in terms of that I have a stage fault vehicle. So I have a vehicle that I bring out, it would be on a lowboy trailer. And on the lowboy trailer, I have a circuit breaker and I have a motor operated ground. So what would happen is when the fault occurs, I've already got the circuit breaker connected to the transmission line, and the circuit breaker that's to test the stage fault circuit breaker that I've got set. Let me annotate it. What I'm thinking of is this. Here's my transmission line, and I've got a circuit breaker at either end of the transmission line, and I want to test this. So what I'm going to do is I'm going to have a trailer here, and this trailer has a circuit breaker on it, and then one end of this goes to ground, and I should put it, I got a motor operated, this is a motor operated disconnect switch right here, and the other end goes up to the transmission line here. So what happens is I close this motor operated disconnect switch with this circuit breaker already closed, and as soon as I close this motor operated disconnect switch, I get a signal to open this breaker. So if the relaying doesn't work up here, I've still isolated the fault by opening this breaker here. So this is my stage fault test. This is a trailer I'm bringing in with all my equipment to do the stage fault testing. This is all my monitoring equipment. This is all my fault testing equipment. And I'm verifying that when a fault occurs, I expect this and this to open at the same time that this opened. On the other stage fault tests we're doing, like in an operating area, if this is make this a 230 kV line. The other tests where I'm doing load testing, I don't have to do the fault testing on the 230 kV line. I could do the fault testing at a neighborhood substation. So I've got a 69 kV line. And what I'm trying to do is demonstrate that my models are adequate. So what I'm going to do is monitor all the load and current and voltage at a 69 kV substation, and put this on a 69 kV line where I'm expecting that I'm not going to trip the line off, but my stage fault is going to give me all my load data I need. So this could be faults on the 500 kV system or the 345 kV system or the 230 kV system. And the load testing would be at a lower voltage, 138 or 69 kV, with less risk to the power grid.
You could also use that data to calibrate your transmission steady state and dynamic models as well.
Yes, yes, yes. So there's a lot of really good things we could do, and there's a lot of good products out there we could be using, and somehow we have to get enthusiastic and start putting all these things in play.
One last question for me. You were explaining the, I don't remember, the thing that you connected at the end of the lines to increase the voltage.
Oh, the solenoid series reactor.
Right.
if I have a transmission line today, what I do is I put a circuit breaker in here, and then I have the transmission line run from here to someplace else. So I'm showing this is a transmission line with circuit breakers on both ends of the transmission line. And then if I put a solenoid series reactor in right here, and I put a solenoid series reactor in here, under normal conditions, the impedance of this reactor would be, under load conditions, the impedance of this reactor would be, say, 1 ohm. So this is a 1 ohm reactor, and this is a 1 ohm reactor. And what I'm looking at right here, this is the core and coil assembly up here, and this is the plunger that moves up and down. So when the plunger changes position, this changes from a 6 ohm reactor to a 10 ohm reactor.
Oh, it's almost like a variable resistor, right? Like a rheostat.
Yeah, but it's all inductance. A rheostat would be resistance, and this is inductance.
Right.
And so this is going to change from 1 to 10 ohms. And when this changes from 1 to 10 ohms, what happens is I change the circuit impedance so that now when a fault occurs, the impedance is about, well, the voltage at the fault is 0. And when I put the solenoid series reactor in, that 1 ohm is going to stop me from going from 0 voltage to some other voltage, like maybe this is showing like 25% voltage on the bus closest to the fault. And when it changes position, it pulls the voltage up to 70%.
So if you have any further questions after the webinar ends, feel free to email Tony or myself. You can also connect with us on LinkedIn and send a direct message that way. We published an article recently under Tony Sliva's name on wide area blackout. So if you want to join in the conversation there, it is on Energy Central. If you aren't a member of Energy Central, it's a really great social media networking tool for people in the electric power industry. So feel free to connect with us there as well.
If there are no more questions, thank you for attending. I hope you had as much fun attending this as I had putting it together. And hopefully you'll attend one of our future webinars. Thank you.